Oh, you're not plugged in to the HDMI.
Okay, students, welcome. This is the last lecture for the semester, and we're going to try to look at the polar structure of the water molecule today. But before we do that, let me remind you that we're going to have a regular homework assignment tonight, homework 19, concerning concepts in this lecture. And also, we're going to have a mega review homework, and I'm going to convert that into some 2 or 3 bonus points. So there might be 30 questions on the mega review, and I'll convert it to 2 or 3 bonus points. Okay. And then in class today, we're going to do regular clicking, last regular clicking of the semester, and we're going to do a clicking review, self-paced, like what you do on exams. Now, that'll be the last 30 minutes of class. All right. Before we get to any of that, I want to mention to you that the Sean Tiernan, are you here? You're breaking my heart. Okay, good. We're waiting for Sean. Apparently, he sent me the information. The schedule page, as soon as I get that, I'll be able to set up the sign-ups page. And students, you can look at it right now. Here's a picture of Jacob Paul. And there's... Sean, what day are you going? Ooh, so finally there's somebody on Sunday. All right, good. That was the one day that we didn't have anybody going. So we got Friday, Saturday, Sunday, Monday, Tuesday, and Wednesday. Good variety. You can go ahead and look at it. And that sign-up process, the Buffalo Stampede, will proceed tonight at 9 o'clock. All right? And so that'll be good. All right, last time we were talking about molecules and stuff. We didn't get to this picture. This is a picture from The Lord of the Rings, the Big Battering Ram. This phrase, Avogadro molibus urbem, is a Latin phrase. It means it's used for battering rams. So we're going to talk about this keyword, molibus. And what that means in Latin is it's related to the concept of a large, shapeless, huge bulk. So that big battering ram in The Lord of the Rings was a big, basically a big piece of iron. And literally this Latin phrase, Avogadro molibus urbem, means literally attacks huge bulk on city. So now the suffix that we use in English, cule, C-U-L-E, at the end of a word, denotes smallness. So the word molecule is means a small part of the molibus or the moles, right? So a small part of the shapeless bulk. In other words, a molecule, what we now call a molecule. Here's a picture of the methane molecule, CH4. That black sphere in the middle, Christiana, is a carbon, and the 4 white ones, if you look at that, they form kind of a pyramid, or what we call a tetrahedron. Okay, those are hydrogens, 4 hydrogens. Now, the guy that put all this on a theoretical basis about 100, or actually 200 and something years ago, was this guy, Lorenzo Romano Amadeo Carlo Avogadro, who lived in the year 1776, the year of our independence, until 1856. Interesting guy from a family of lawyers in Turin, Italy, northern Italy. And it was his opinion, his principle, Avogadro's principle, that formed the basis for our current understanding of what molecules do. Now let's look at the concept of molecule first. We're going to do shapeless bulk, moles, in a few minutes, but molecule first. It means, it is the word that we use for the tiniest constituent of a large sample. Now, large sample, that's the molybus. Okay? We measure the molecule mass in atomic mass units. Now, we didn't get to this last time, so let's go over it carefully. The atomic mass unit, it's not a gram. You can convert it to a gram, or a fraction of a gram, fraction of a kilogram, any other mass unit you want. But it's the normal one that we use for measuring atoms and molecules. Is based on carbon. And our current understanding of carbon, the most abundant molecule, the most abundant type of carbon in nature is carbon-12. That means it has 6 protons in the nucleus and 6 neutrons, total of 12 items in the nucleus. So we call it carbon-12, and we say that carbon-12, that particular form of carbon, among the different versions, is exactly 12. And that means, for instance, that common hydrogen is 1 atomic mass unit. Because hydrogen is just 1 electron, that's hardly anything, and then 1 proton, that's most of the mass of a hydrogen atom. But there are other isotopes of hydrogen in nature, other forms. There's a form of hydrogen called deuterium, D-E-U-T-E-R, deuter. That's from the Greek for 2. And what it means is, in the nucleus, it's not just one object, a proton, it's a neutron and a proton bound together. Now, in nature, the deuterium atom is considered a form of hydrogen, what we call an isotope. Same chemical behavior, different mass because of the nucleus. A neutron in the nucleus doesn't change the electromagnetic interaction, but it does change the mass of the atom itself. And it's considered a heavy hydrogen. If you have ever heard the word heavy water in reference to nuclear reactors, like these guys over in Iran that are trying to build a nuclear weapon, they're trying to refine uranium and stuff. A lot of times they want to build something called a heavy water reactor. It uses water that's made up of deuterium atoms, not just regular hydrogen atoms. And we can separate deuterium. We've been able to do that for 70 odd years from water. And there's deuterium in every glass of water that you drink. Just not a whole lot. But we can filter it out. It's not that hard. And we get a whole bunch of it. We can use it for its special properties. Tritium is another isotope of hydrogen. And tritium for 3. That means there's 3 objects in the nucleus. 2 neutrons, 1 proton. All hydrogens, 1 proton in the nucleus. All right. Now, helium comes in 2 different flavors. Helium-3 and helium-4. Now, every helium atom has 2 protons in the nucleus, but helium-3 has a neutron as well as 2 protons. Helium-4 has 2 and 2, right? And we, so we can rate the mass of the helium atom as 3 atomic mass units or 4 atomic mass units. We can do the same for molecules. For instance, CO2. CO2 is 44 AMUs, 44 atomic mass units, usually. All right? So the most common form of carbon and the most common form of oxygen, which is oxygen-16, will give you 44 atomic mass units for the molecule. Matter of fact, let's take a look at the periodic table in reference to CO2. Okay, so here's the periodic table, and carbon and oxygen are up in the northeast corner. Let's focus in on that. So here's the upper northeast corner. So I'm burning in 2 little boxes, rectangles around the carbon and the oxygen. So if you look at those, the specs, Nicole, for carbon and oxygen, you'll see that carbon is rated at atomic mass of 12, 12.0 on this particular periodic table. And then 2 blocks over from that is oxygen, and that's rated at 16.0. All right? And so, and there's a bunch of other stuff. You know, periodic tables are not all uniformly the same. You know, this one has a little bit of electronic structure notation in the bottom right of each cell, but basically the atomic masses there are 2 16s, 2 oxygens for carbon dioxide, so that's 32 atomic mass units, and then another 12 for 1 carbon in CO2, total of 44. Now, molybus, the big shapeless bulk, large sample of an element. These we measure in the macroscopic scale, grams, kilograms, and so forth. And as you know, the gram is based on cubic centimeter of liquid water for the mass. Now, here's where Professor Avogadro comes in. He said in 1811, 106 years ago, that if you take equal sized containers of CO2 and hydrogen, you know, so a 2-liter bottle of CO2 and a 2-liter bottle of O2, oxygen. And if they're at the same temperature and the same pressure, so they're in the same room, okay, and they're at the same pressure, they're going to have the same number of molecules. And he believed that that would be true based on the idea that all molecules of a certain substance, whether it's CO2 or oxygen or methane or any other molecule, they would all be the same. And so all CO2 molecules are the same. There's no difference between them. And he said, all right, if they're all the same, then they ought to, and if they all obey F equals ma, then we ought to have this property that equal volumes contain equal numbers if they're at the same temperature and pressure. And we've since verified that. Now, that being the case, it's possible to say, or to ask this question. All right, instead of equal volumes, what if I control the mass and I make the mass some multiple of the atomic mass? All right, so the logical thing is, if I make the mass of my shapeless bulk the same number of grams as my individual molecule is of atomic mass units, so for instance, CO2, 44 atomic mass units for a molecule, how many molecules do I have in 44 grams of it? So if I make my molybus 44 grams, how many of my 44 atomic mass unit molecules are there in that? And if you go back to the periodic table and look at aluminum, a metal, if you have 27 grams, that's the atomic mass of aluminum in nature. How many, if Avogadro is really true, if he's really correct, then I should have the same number of aluminums as I have CO2s. If I have 27 grams of aluminum equal to the atomic mass of aluminum atoms, I should have the same number of CO2s. All right? And it works out that that's the case. In the metric system, that number is, so if you go 44 AMUs, 44 grams for CO2, 27 AMUs, 27 grams for aluminum, and so on and so forth for every atom or molecule. It turns out that the number is the same, and it works out in the metric systems to 6.022 times 10 to the 23, and that is a ginormous number. That's Avogadro's number in the metric system. Now, if you're in the English system, using pounds or something like that, or ounces, it would be different. It would be a bigger number. But in the metric system, this is what it is. right? You think in terms of atomic mass units, and you can get that atomic mass units by doing chemistry lab experiments, getting the ratio of the masses of your two samples. You can figure out all the ratios, CO2 and H2O and so on and so forth. And then you say, okay, 44 AMUs, 44 grams, right? So the 44 grams would be the molar mass, MOLAR. Now let's go and take a look at a side note here on carbon. If you look carefully at a periodic table, a lot of times you'll see that this number down here is not exactly 12. I mean, carbon is defined to be the basis of the atomic mass system, the atomic mass unit. So why doesn't the periodic table say exactly 12.00 for carbon? Well, the answer to that is that in nature, there are 3 different isotopes, right? 3 different flavors of carbon. Now, most of the carbon in nature is carbon-12. And what I've got here is a little kind of randomly shaped bag of 6 neutrons and 6 protons, all right? And the notation is a 12 upstairs and the capital C, or a 12 upstairs, 6 downstairs, and a capital C, okay? And those are what we would call the isotope notation for carbon-12. Now, in nature, we also find a bunch of these. Carbon-13. Now this one, I made a picture, a slightly different picture. 6 protons, 7 neutrons, total of 13. So this is a heavier carbon. And believe it or not, this flavor of carbon that we see in nature is related to carbon dating, radiocarbon dating that we use for dating, like Indian artifacts and caveman artifacts and stuff like that. Carbon-14 also is related to that. And these are the three stable isotopes in nature of carbon. Carbon-14 has 6 protons, as all carbons do, but it has 8 neutrons. Right? Now, the interesting thing about these, the mass of each of these atoms, Natalie, is going to be different, but the chemical properties are going to be the same, because the chemical properties are controlled by the electrons that are in orbit, there's no gravitational. You don't really have to work with the gravitational forces for an atom. You only have to work with the electrical forces, and that's protons and electrons. So adding in some neutrons doesn't change any of the chemical reactions or stuff like that, except maybe the speed. The speed of the chemical reaction might be a little bit slower, simply because it's a heavier molecule, heavier atom, but not by much. Okay, so the most abundant form in nature is carbon-12, and these other 2 are kind of rare. Those are, but we can measure them. We can isolate them using physics equipment. Using F equals ma, we can sort them out. The carbon-12s will shoot a little bit further, and they'll come to ground a little bit further down the line. The carbon-13 a little bit shorter, carbon-14 a little shorter than that, so on and so forth. So that's the idea of nuclei and isotopes, and it's a part of the periodic table. Now, I want to go back to the molar mass of another compound. Let's try this on clickers. And this will be our first clicker question of the day. And simply compute the molar mass of nitric oxide. And here's a slice of the periodic table you can use to do that. So think about nitric oxide. One nitrogen, one oxygen. Something your body needs. Your body makes it. Nitrogen. Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, what's the situation with the answers here? Okay, pretty good. Most of you guys got that one right. Here's the answer, 30.006. And for those of you that got it incorrect, here's the calculation. You take the one nitrogen atomic mass, so 1 mole of nitrogen, 14.007 grams, and 1 mole of oxygen, you read that across from the periodic table, 15.99, and you just add them up, and you get 30.06. And that's grams in a mole, a molybus of nitric oxide. Question? Repeat your question. Because we're asking about the molar mass. We're asking about, what is your name again? Lanisha. Lanisha, what we're asking about is the molybus, the big blob. And what we call an official metric system molybus, 6.022 times 10 to the 23 molecules, is going to be the same number of grams as an individual molecule is AMUs. Okay? And if you go by atoms, the nitrogen, every nitrogen atom is 14.007 AMUs, approximately. Therefore, molybus, on Avogadro's number of that, is going to be 14.007 grams. Okay? So the question is about the molar mass, not the atomic mass or the molecular mass. Molecular mass would be 30.006 AMUs. But we're asking about the mass of an entire mole, an entire molybus, an entire shapeless bulk of it. Okay? And that's why it's in grams. All right. Energy levels. Let's talk about carbon and its electron orbitals. Now, we're going to use this to understand bonding, and specifically the bond structure of water. But we're going to talk about carbon because carbon is kind of an interesting atom. The first energy level, ground state, orbital angular momentum, the other dynamical quantity. Orbital angular momentum is 0, and the intrinsic spin angular momentum is either up or down. There's 2 angular momentum states, spin angular momentum states, S equals up or S equals down. All right? And so that means that in the N equals 1 energy level, the total population of electrons is 2. Okay? You can, at that energy level, you can either have an up electron or a down electron. And so I will sketch that in on my first energy level. Here's my circle, my energy level. And then I put a little blue dot here, a blue circle, to represent an electron. And Lexi, this one up here is an up arrow. And then this one down here is a down arrow to represent, the up and the down. So this means that we think of it, you can think of an up arrow as angular momentum, the thumb representing the angular momentum, so spinning counterclockwise as viewed from above. Down angular momentum would be spinning clockwise as viewed from above. All right. Now, we don't think that electrons, you can't really see that they're spinning, but they still seem to have this angular momentum. Energy level, N equals 2. Next energy level up. Carbon's got some electrons there in the N equals 2 shell. Okay, so now at this higher energy, you can have either L equals 0 for orbital or L equals 1. And each of the L equals 1 orbitals can be split into 3 suborbitals. All right, so, and each of those can have an up or a down. So the bottom line is another 6 plus 2. So 2 for L equals 0 and another 6 for L equals 1. Okay. You have an up and a down for L equals 0, and you have 3 ups and 3 downs for L equals 1. So a total of 8. And, 8 orbital states available. And here, now this is what is possible on N equals 2. But carbon only has 4 atoms up, carbon only has 4 electrons up there. So because a neutral carbon, 6 protons, 6 electrons. Okay, 2 of the electrons are down in N equals 1. And then, and I've got 4 more to work with, so those go into N equals 2. And that means that you've got to, you're going to have 4 of those possible states unfilled. Now, atoms don't like to be going around with an energy level unfilled. They like it to be filled. That's what they like to do. All right? The outer electrons in the outermost shell are called the valence electrons. And those are the ones that are used in bonding. In other words, these are the ones that are easiest to be stolen by another atom or to be shared in a cooperative manner with another atom. That also forms bonds. All right? So erase 2 of those pairs. 2 of the pairs in carbon are going to be absent. All right? So you got 1 pair of up and down, and here's another pair of up and down at N equals 2. So valence electrons, the outer ones are the so carbon has 4 valence electrons. Valence means moving, motion. Okay, so these are the ones that are easiest to steal, the easiest to move around. And so let's talk about bonding. And here's the thing this is the main concept that we believe is true about atoms bonding. Other elements will react with another, 2 elements will react, and one of them will either gain or lose electrons so that the outermost energy level is the same as one of the noble gases. All right, so underline that word noble gases, and let me tell you what noble gases are. Noble gases are these elements in the rightmost stack of the periodic table. Now, all the elements in that stack have common physical properties. Okay? Very similar physical properties. And one of them is they don't react with stuff. They're noble. They're aloof. They don't react with carbon. I mean, they don't form bonds. They don't form bonds with Jack. Well, we can force helium and neon and stuff to make compounds, but they don't last very long. They decay. Okay? And that's because the outermost energy level is full. So for helium, N equals 1, that's all they need for the ground state. So N equals 1, 2 electrons, and that's all that a normal helium has. So helium is as happy as the proverbial clam. Okay? It's got 2 electrons. Outer energy, the first level, energy level is shared, or is full. It's happy as a clam. And it's not going to bond with stuff for that reason. Right? Neon. Neon has all of n equals 2 full. So that means it's got 10. It's got 2 in n equals 1 and another 8 in n equals 2. Right? The second energy level. And that means a total of 8. So that energy level is full. So neon is happy as the proverbial clam. And what I'm going to show you is how carbon and oxygen fill their outer energy levels, or reformat their energy levels so that they have noble gas type configurations. So let's take a closer look at it. Okay. The electron theory of chemical bonding states that only the electrons in the outermost orbitals are involved in chemical reactions. And that's because they're not as tightly bound. Think of it as like a spacecraft orbiting Earth. Now, that's a gravitational system. But the further you are out, the easier it would be for you to get to Mars, to another planet. You know, if you're at an altitude of 100,000 miles, you're most of the way to the, well, you're almost halfway to the moon. All right? And so to get all the way to the moon, you wouldn't need a lot of rocket fuel. If you're already out there at 100,000 miles altitude, you just need a little bit of, but if you're at 200 miles from the surface of the Earth, it's going to take a lot of rocket fuel. It's the same thing here. If you're out there at an outer energy level, it's going to be easy to steal you or easy for you to be shared. All right? And it's easy for us to put things in orbit and at exactly the right point between Earth and Moon where the gravitational force is exactly balanced. So it's kind of interesting. So the outer orbital electrons, however many there are, the valence electrons, they're the ones that are mostly responsible for the chemical properties of an element. Right? So the fact that gold does not tarnish, that's a chemical property. The fact that iron does rust, it oxidizes, that's a chemical property. The fact that carbon makes an enormous number of compounds, including the ones that we need for life, you know, we're a carbon-based life form, they say. That's all because of the outer 4 valence electrons of carbon. Now, let's take a look at the first stack on the left of the periodic table. In other words, the hydrogen stack. Those ones over there are, the way to think about those are, they have 1 valence electron. Everything is full except for that 1 extra electron. So they've got, you know, n equals 1 full, n equals 2 full, n equals 3 full, plus 1. So n equals 1 full plus 1 is lithium. That's the third one. N equals 2 full plus 1. N equals 2 full is neon. Neon plus 1 is sodium. And so on and so forth. So what happens is that one little old electron out there is easy to steal. It's easy to borrow. It's easy to steal. All right? And what happens is that, for instance, sodium, that valence electron of sodium, it's weakly bound. It's out there. Chlorine is happy to steal it. And when chlorine steals that electron, zoop, 5-finger discount, the chlorine becomes a negative, the sodium becomes a positive. They're both ions. They bond together. It's an ionic bond, and that is what we call table salts, NaCl, sodium chloride. It's an ionic bond. It's an interaction, a bond between 2 ions. Now, I'm going to show you a different kind of a bond. or an example of a different kind of a bond for carbon and oxygen. All right, so now here's the periodic table, and take a note. The carbon and oxygen are over here. They're just a hop, skip, and a jump from the rightmost column, the noble gas column. All right, so let's focus in on the top right again of the periodic table. Okay, so the noble gases, this rightmost stack, and then this next stack is called the halogens. There's all kinds of names for the different stacks and stuff. But let's take a look at carbon. Carbon's over here, and if you think about it, ching, carbon is 4 bumps away from neon. 1 bump away, nitrogen. 2 bumps away, or 2 more electrons away, oxygen, fluorine, and then neon. So here's your concept, your bonding concept. If carbon can grab or share 4 electrons from 1 or more atoms, it will form a bond. It will be happy. All right? Now, oxygen is right here. All right? And oxygen, it just needs 2. Ching. Get me 2 extra electrons for an oxygen, and it'll have a filled N equals 2. So if I add 4 to carbon, I'll have a filled, go ahead and make a note of that. Add 4 to carbon, your N equals 2 is full. Just like all neon. Oxygen, add 2 electrons, your N equal 2 will be full. Just like all neons. All right, so carbon by itself will be, neutral carbons, happy to, but if it's in the neighborhood of something else that it can bond with, it'll bond. All right, and we happen to be able to get CO2 from oxygen and carbon bonding together. Now, there's one more thing I want to show you. Carbon is kind of unique, Kane, because carbon is 4 units away from neon. All right? So if carbon can get 4 electrons, it'll have the same outer shell as neon has. But you can also strip 4. All right? If you take away 4, you can get back to helium. Now, look at my animation here. I'm going to burn them off step by step. Here we go. Let me burn off 1. Boron. 2. Beryllium. 3. Lithium. And all the way back over here to helium. So if I subtract those 4 valence electrons, if I borrow those away from carbon, carbon will be happy. It'll be in another happy state. Because it'll have an outer shell, N equals 1, that's full. And that will be like helium. All right? So your first note is carbon gains 4, neon-like outer energy shell, N equals 2 full. Second note, oxygen gains 2 electrons, outer shell, N equals 2 is full. Third note, carbon loses 4. Like neon, outer energy shells, N equals 1, and it's full. All right, so carbon can go either way. Lose 4 or gain 4, and that's one of the reasons it combines with so many things. Now, let's take a look at the specifics. All right, so here's carbon 12. And let's do N equals 1 and N equals 2. All right? And we know that there's 2 electrons down at N equals 1, normal configuration, and 4 in N equals 2. And oxygen, similar. N equals 1 has 2 electrons. And it's got 6 electrons in N equals 2. Right? Now, we either want to have n equals 2 loaded up with 8, or we want n equals 1 loaded up with 2. Now they've both got n equals 1 loaded up with 2, so that's good. So if we strip one and use it to fill the other, we're golden. And that's what we're going to do. So here we go. We're going to take those 4 carbon outer electrons, the valence electrons, and go bye-bye with them. All right? So they're going bye-bye. See you later, alligator. But we're slotting them over here to the oxygen. All right? And now oxygen feels like, yeah, baby, I've got n equal 2 full. And carbon's over here saying, ooh, nice. N equals 1 is full. I'm feeling like helium today. And each of the oxygens is thinking, ooh, this feels like neon. And so that's what they like. That's what carbon and oxygen like to do. That's one of the ways that they form molecules. That's what we call carbon dioxide. All right? Now, this is an example of something called covalent bonds. And I'm going to give you a picture of a real simple covalent bond next. Camille, do you have a question?
In the picture, if carbon-12 only had 4 electrons on the outside?
Mm-hmm. So we bolted them over to the oxygen. Okay? Now this is kind of a rough picture because, Camille, all these electrons are actually behaving like waves. But still, this idea of sharing and stealing and borrowing stuff and outer shells full and stuff, that still all works. It's all countable. We can still count even though they're waves. Here's the waves. Let's look at the wave functions of the electron. And we're going to look at a picture of hydrogen atoms. And hydrogen forms a molecule, H2. Okay? The gaseous form of hydrogen is, under most conditions, is 2 hydrogens bonded together. Now, when 2 atoms are far apart, their wave functions look like this. And so so what you're looking at here, that's the Greek letter psi, P-S-I. Okay? That's the symbol for the wave function. And you're looking at 2 of them. And they look like 2 mountains, really sharp, 2 volcanoes. All right? So that picture, that first picture, shows you the wave functions of the electron around each of 2 atoms of hydrogen. And when they're far away, those wave functions don't overlap that much. Now, right here where my arrow is pointing to, Elizabeth, the wave functions are flat right there. It's not because there's destructive interference. It's because the waves are really pokey there. They're so far apart, they don't really have much amplitude there. Okay? It's not that I've got a crest and a trough canceling to give me flat water. It's just that I don't have any waves there. They're so far apart, the wave amplitude is pretty low. Now, right here, by the center of the atom, yeah, you got a big amplitude. But it's way over here to the left. And this other atom, it's way over here to the right. Okay, so we don't have a lot of overlap. But it is possible to move them closer. And if they move closer, you do get overlap. Question?
So you said that the peaks are like
The peak corresponds to the location of the nucleus of the atom, in this case, the hydrogen atom. Okay? And the shape of the red curves is the amplitude of the electron wave. It actually diminishes, it gets weaker as it goes away from the nucleus. Now, if they overlap, if they get close enough, look at that. That's 2 waves just about to meet in the middle of the ocean. So you can say to yourself, what's this action in between? Now, quantum mechanically, in quantum physics, what we construct the amplitude, and then what we have to do to make any measurements, we have to use the square of the amplitude. Remember, the square of the amplitude is the thing that affects that is the measure of the energy of electromagnetic radiation, and also it's related to sound as well. All right? So right here, here's the amplitude. I mean, if the wave was a wave in the ocean, this would be like a photograph of two waves coming close together. Right? But these are electron waves. So we have to square it, and we still have high water here. The square is still above zero. Now up here, in between, halfway in between the two atoms, flat water. Halfway between down here, when they're close, that ain't flat water, my friends. That means you've got an electron there. That is, after a lot of calculus, using imaginary numbers, that is what we would call constructive interference. That is the covalent bond, the sharing. So now the hydrogens, each hydrogen feels as if it's sharing or it's got two electrons. But they both feel that way. And they form a molecule. Right? So they're both feeling like they're both feeling like helium now. Right? Because they're sharing. And my wonderful students, underline the word constructive interference, because this is a quantum effect. Okay, last set of slides is this. Water molecule. Over on the left side, above and below, I've got a couple hydrogens, a +1 and an electron. +1 and an electron down below there. And over to the right, I've got a +8 oxygen nucleus, and I got kind of 8 electrons kind of sprinkled around randomly. All right? Now, the electrons are behaving like waves, not like little dots, like little baseballs, but we can still use this diagram to think with. I'm going to bring the two hydrogens in close. I'm going to try to get the hydrogens in close to the oxygen now and get some overlap. Right now, there's zip overlap, zip zap. But if I bring them in closer, which I'm about to do, I'll bring them in close so that two of the blue electrons overlap. All right? But when I do that, the electrons are going to tend to shift to the other side, right? Because I'm going to be bringing in this valence electron here and this valence electron here from the hydrogens, and that's going to, for instance, make this guy here bop over to the other side of the oxygen. So let me move it. Watch. Here's an animation. Bing, there it goes. All right, so it's over there. Let me bring these other ones in. I'm overlapping on the upper left and right below the oxygen. And my wonderful students, I've now got hydrogen electrons overlapping with one of the electrons from the oxygen. And now the hydrogen feels like, dude, I got two electrons. And the oxygen is feeling like, dude, I've got 10 electrons. Okay? So they're both really HAPPY. All right? And that is why water has this polar structure. Our life on Earth depends on it. The polar structure means that you have a positive end and a negative end. And that is how water binds so easily. It dissolves so many other compounds like proteins, carbohydrates, and so forth. All right. Your final exam is going to cover everything up to this slide. Now what I want you to do is we're going to get your clickers out. We're going to do another clicker session. We're going to hand out some handouts. And you'll be able to do those right now in class. We'll set up the clicking session in just a second. And so, Darian, you can start handing these out. And just work on your clicker questions. And as soon as I start the session, you'll be able to type them in at your own pace. So let me turn the lights up here. No, she's fine. She's good. Don't worry.